Today we're diving into the fascinating world of memory mapping. Whether you're a tech enthusiast or just curious about how computers handle data, understanding memory mapping is essential. This concept is at the heart of how modern systems manage and access information efficiently. In this video, we'll break down what memory mapping is, why it matters, and how it's used in everyday computing. By the end, you'll have a clear grasp of how memory mapping powers everything from your favorite apps to complex operating systems. Let's get started with the basics and see why this topic is so important in the digital age. What exactly is memory mapping? In simple terms, memory mapping is a technique that allows a computer program to access files or devices as if they were part of the computer's main memory. Instead of reading and writing data through traditional file operations, memory mapping lets programs treat data as if it's already loaded in RAM. This approach can significantly speed up data access and manipulation, making it a popular choice for high-performance applications. Let's explore how this works in practice and why it's so efficient. Memory mapping works by creating a direct association between a file or device and a region of the computer's memory. When a program requests access to a file, the operating system maps the file's contents directly into the program's address space. This means the program can read or write data simply by accessing memory locations, without the need for extra file I/O operations. This seamless integration not only boosts performance but also simplifies code, making it easier for developers to manage large datasets or interact with hardware devices. Key part of memory mapping is virtual memory. Virtual memory allows computers to use more memory than physically available by using disk space as an extension of RAM. Memory mapping leverages this by mapping files or devices into the virtual address space of a process. This means programs can work with large files or datasets without worrying about physical memory limits. The operating system handles the details, ensuring that only the necessary parts of a file are loaded into RAM as needed, optimizing both speed and resource usage. Remapping offers several important benefits. First, it can greatly improve performance by reducing the need for slow file I/O operations. Second, it simplifies programming, since developers can access files as if they were arrays in memory. Third, it enables efficient sharing of data between processes, since multiple programs can map the same file into their address space. These advantages make memory mapping a powerful tool for building fast, scalable, and reliable software systems. Operating systems make extensive use of memory mapping. For example, when you launch an application, the OS often maps the program's executable file into memory. This allows the program to start quickly and access its code and data efficiently. Memory mapping is also used for managing shared libraries, device drivers, and system resources. By leveraging memory mapping, operating systems can provide fast, secure, and flexible access to files and hardware. Developers often use memory mapping to handle large files or datasets. For instance, database systems and multimedia applications rely on memory mapping to process gigabytes of data without loading everything into RAM at once. This technique allows applications to access only the parts of a file they need, reducing memory usage and improving responsiveness. As a result, memory mapping is a go-to solution for building high-performance, data-intensive software. Remapping isn't just for files, it's also used to interact with hardware devices. For example, device drivers use memory mapping to communicate with graphics cards, network adapters, and other peripherals. By mapping device memory into the address space of a process, software can control hardware directly and efficiently. This approach is essential for achieving high-speed data transfers and real-time performance in modern computing environments. There are several types of memory mapping, each serving different purposes. The most common are file-back mapping and anonymous mapping. File-back mapping links a file to memory, allowing changes to be saved back to disk. Anonymous mapping, on the other hand, creates a memory region not associated with any file, useful for temporary data storage. Understanding these types helps developers choose the right approach for their application. File-back mapping is perhaps the most familiar form of memory mapping. When a file is mapped into memory, any changes made to the map region can be written back to the file on disk. This is especially useful for applications that need to update large files efficiently, such as databases or image editors. File-back mapping ensures data consistency and allows multiple processes to share access to the same file, making collaboration and data sharing straightforward. Anonymous mapping creates a region of memory that isn't tied to any file. This is ideal for temporary data storage, such as program variables or buffers. Since the map memory isn't saved to disk, it's automatically released when the program ends. Anonymous mapping is commonly used for tasks like allocating large arrays or managing temporary caches, providing flexibility and speed without the overhead of file operation. Remapping can be either shared or private. Shared mapping allows multiple processes to access and modify the same memory region, making it perfect for inter-process communication. Private mapping, on the other hand, gives each process its own copy of the mapped memory. Changes made in private mappings aren't visible to other processes, which is useful for tasks that require data isolation. Choosing between shared and private mapping depends on your application's needs. Operating system plays a crucial role in memory mapping. It manages the mapping process, keeps track of which memory regions are associated with which files or devices, and handles page faults when data needs to be loaded into RAM. The OS also enforces security, ensuring that only authorized processes can access certain memory regions. This careful management keeps your system running smoothly and securely. When a program tries to access a part of a mapped file that isn't currently in RAM, the operating system triggers a page fault. The OS then loads the required data from disk into memory, a process known as demand paging. This on-demand approach ensures that only the necessary data is loaded, saving memory and improving efficiency. Page faults are a normal part of memory mapping and are handled seamlessly by the OS. One of the biggest advantages of memory mapping is its impact on performance. By allowing programs to access files as if they're in memory, memory mapping eliminates the need for slow read and write operations. This results in faster data processing, lower latency, and better overall system responsiveness. For applications that handle large datasets or require real-time performance, memory mapping is often the best choice. While memory mapping offers many benefits, it also introduces security considerations. The operating system must ensure that only authorized processes can access mapped memory regions. Improper use of memory mapping can lead to data leaks or unauthorized access. Developers need to follow best practices, such as setting appropriate permissions and using secure APIs to keep data safe while taking advantage of memory mapping's power. Databases are one of the most common users of memory mapping. By mapping database files into memory, database engines can quickly access and update records without loading entire files into RAM. This approach improves performance, reduces memory usage, and allows for efficient multi-user access. Many high-performance databases rely on memory mapping to deliver fast, reliable service to users. Multimedia applications such as video editors and image processors often use memory mapping to handle large media files. By mapping files into memory, these applications can process high-resolution images or long videos without running out of RAM. This technique enables smooth playback, fast editing, and real-time effects, making it a favorite among creative professionals. Embedded systems like those in cars or smart devices use memory mapping to interact with hardware efficiently. By mapping device registers into memory, software can control sensors, actuators, and other components directly. This approach reduces latency and ensures real-time performance, which is critical for applications like automotive control systems or IoT devices. Networking software often uses memory mapping to manage buffers and data streams. By mapping network buffers into memory, applications can send and receive data quickly, reducing overhead and improving throughput. This technique is especially useful for high-speed servers and network appliances that need to handle large volumes of data with minimal delay. Most operating systems provide programming interfaces for memory mapping. In Unix-like systems, the mmap function is commonly used, while Windows offers the Map View of File API. These interfaces allow developers to map files or devices into memory with just a few lines of code. Understanding these APIs is essential for building efficient, high-performance applications that leverage memory mapping. In C and C++, memory mapping is a powerful tool for handling files and devices. Developers use system calls like mmap to map files into memory, allowing direct access to file contents. This approach is especially useful for performance-critical applications such as databases or scientific computing, where speed and efficiency are paramount. Python also supports memory mapping through the mmap module. This module allows Python programs to map files into memory and access them as if they were byte arrays. Memory mapping in Python is popular for processing large text files, binary data, or working with memory map databases. It combines ease of use with the performance benefits of memory mapping. Java provides memory mapping capabilities through the Java Neo package. Developers can use the map byte buffer class to map files into memory and access them efficiently. This feature is widely used in Java applications that need to process large files, such as search engines or big data tools, offering both speed and scalability. Many other programming languages, including Go, Rust, and C, offer memory mapping support through their standard libraries or third-party packages. This widespread availability makes memory mapping a versatile tool for developers across different platforms and languages, ensuring that high-performance data access is within reach for any project. Despite its many advantages, memory mapping comes with challenges. Managing large mapped files can lead to address space fragmentation, and improper use can cause resource leaks or crashes. Developers must carefully manage mapped regions and handle errors gracefully to avoid problems. Understanding these challenges is key to using memory mapping effectively and safely. To get the most out of memory mapping, developers should follow best practices. This includes unmapping memory regions when they're no longer needed, handling errors properly, and setting appropriate permissions. By following these guidelines, developers can maximize performance and reliability while minimizing risks. Memory mapping can be used in multi-threaded applications to share data between threads efficiently. However, developers must ensure proper synchronization to avoid race conditions or data corruption. Using locks or atomic operations helps maintain data integrity when multiple threads access the same mapped region. Shared memory mapping is a powerful technique for interprocess communication (IPC). By mapping the same file or memory region into multiple processes, programs can exchange data quickly and efficiently. This approach is widely used in high-performance computing, real-time systems, and server applications. File systems themselves often use memory mapping to cache frequently accessed data. By mapping file system metadata and data blocks into memory, the operating system can speed up file access and improve overall system performance. This behind-the-scenes use of memory mapping benefits all users, even if they never interact with it directly. In cloud computing environments, memory mapping is used to manage large datasets and enable fast access to remote files. Cloud storage providers often use memory mapping to cache data locally, reducing latency and improving performance for users around the world. This technique is key to delivering responsive cloud-based applications. Virtual machines use memory mapping to manage guest operating systems and virtual disks. By mapping virtual resources into the host's memory, hypervisors can provide fast, efficient access to files and devices. This approach is essential for running multiple virtual machines on a single physical server. Security sandboxes use memory mapping to isolate applications and prevent unauthorized access to system resources. By controlling which memory regions are mapped into each process, the operating system can enforce strict boundaries and protect sensitive data. This technique is widely used in browsers, mobile apps, and secure computing environments. Mobile devices such as smartphones and tablets use memory mapping to manage apps and data efficiently. By mapping app resources into memory, the operating system can launch apps quickly and keep them responsive, even with limited hardware. This technique helps deliver smooth user experiences on devices with constrained resources. Big data applications rely on memory mapping to process massive datasets efficiently. By mapping large files into memory, analytics tools can scan, filter, and analyze data without loading everything into RAM. This approach enables real-time insights and supports the scale required by modern data-driven businesses. Artificial intelligence and machine learning applications often use memory mapping to handle large models and datasets. By mapping training data and model parameters into memory, AI systems can process information quickly and efficiently, enabling faster training and inference. This technique is essential for building scalable, high-performance AI solutions. Virtual reality applications use memory mapping to manage large textures, 3D models, and multimedia assets. By mapping these resources into memory, VR systems can deliver immersive experiences with minimal loading times and smooth performance. This is crucial for maintaining realism and user engagement in virtual environments. Modern video games use memory mapping to load game assets such as textures, sounds, and levels on demand. This approach allows games to offer expansive worlds and detailed graphics without overwhelming system memory. Memory mapping helps deliver fast load times and seamless gameplay, enhancing the player experience. Scientific computing applications such as simulations and data analysis often use memory mapping to handle large datasets and results. By mapping data files into memory, researchers can process information efficiently and perform complex calculations without running into memory limits. This technique is vital for advancing research in fields like physics, biology, and engineering. During system boot, operating systems use memory mapping to load kernel code and essential drivers into memory. This ensures that the system can start quickly and access critical resources right from the beginning. Memory mapping plays a foundational role in getting your computer up and running every time you power it on. Device drivers use memory mapping to interact with hardware components efficiently. By mapping device registers and buffers into memory, drivers can send commands and receive data quickly. This approach is essential for achieving high performance in everything from graphics cards to storage devices. Embedded firmware, such as that found in microcontrollers, uses memory mapping to access program code and hardware registers. This technique allows firmware to execute instructions and control devices efficiently, ensuring reliable operation in everything from appliances to industrial equipment. As technology evolves, memory mapping continues to play a vital role in new computing trends. From edge computing to AI and beyond, memory mapping enables fast, efficient data access in a wide range of applications. Staying informed about these trends helps developers and users make the most of this powerful technique. Let's recap what we've learned about memory mapping. We explored its definition, how it works, and its many uses across different fields. We discussed the benefits, challenges, and best practices, as well as its role in modern technologies like cloud computing, AI, and embedded systems. Memory mapping is a foundational concept that powers fast, efficient, and scalable computing. Thank you for joining us on this journey through memory mapping. We hope you now have a deeper understanding of how this technique works and why it's so important in today's digital world. Whether you're a developer, student, or tech enthusiast, mastering memory mapping can open up new possibilities for building efficient, high-performance applications. Stay curious and keep exploring the amazing world of computing.